last Tuesday in lecture, we were doing redox reactions. And we were looking at the activity series in that table of those oxidations and predicting if we could put two half reactions together to make a redox reaction. Before we do that, I want to go back and do one more type of sample problem. I'd like to go in the back of the chapter and do problem 4.51b. 4.51b, and that's on page 152. And this shows why we want to know oxidation numbers. So here we have a balanced equation. We have 3 moles of iron 2 nitrate plus 2 moles of aluminum metal react to get 3 moles of iron metal plus 2 moles of aluminum nitrate. And we want to know if this is a redox reaction. And if it is, the question states which elements are being reduced and which elements are being oxidized. Okay? And we're going to do that by putting an oxidation number on each atom in this balanced equation. And remember, when we calculate oxidation numbers, we want oxidation number per one atom in a formula, like a polyatomic ion. If there's more than one atom, we want the lower. When we did that stair-step approach, we want the lower the bottom floor. And we all use the top floor, remember, for totals to figure out individual oxidation numbers. So we're going to do that, and remember the oxidation rules that we learned on page 132. So we're going to use those rules to identify oxidation numbers with each of these atoms in the equation. And so, like I told you, whenever you have a salt ionic compound, it's easier just to break it apart into ions. And we don't care if we have 2 ions, 3 ions, it doesn't matter. As long as we get one individual ion, we'll get the correct oxidation number. So I'm going to go ahead and break this one apart. And I know this is iron 2 plus, because if you uncross over the charges, that's where this 2 came from. So that's iron 2 plus. And then this is nitrate from our common ion table. So now it's easier for me to do the oxidation numbers when I break apart the anions and cations of a salt. And so now I know the oxidation number on iron here is a +2 because it's the monatomic ion rule. With monatomic ions, the oxidation number is equal to the charge. But here I have a polyatomic ion, so I'm going to use the addict method. Remember I know that this oxygen is a -2 from the rules. Okay? And since there's 3 of them, 3 times -2 is -6. And I know the top total has to be -1 because this is a polyatomic anion with a negative charge. And so then I say, in the addict, I say, what plus -6 is -1? Oh, it would be a +5. And then coming down, you divide, and I know there's a 1 here. So 5 divided by 1 is a +5. So now I know that this nitrogen is a +5 in nitrate, and this oxygen is a -2. So now I have all the oxidation numbers in that ionic compound. Oh, and this is elemental form of a metal, 1 atom with a solid. So according to those rules, I know the oxidation number is 0 on aluminum there. Okay, now for the products. Oh, oxidation number of a metal, elemental form, 1 atom with a solid, that's also 0. And now once again I have a salt, so I'm going to pull it apart. I'm crossing subscripts. 3 goes here and the 1 goes there, so once again it's nitrate. And since nitrate is nitrate on both sides, I know that's not going to be participating in the redox, it's just a spectator ion because the formula hasn't changed. We'll do it anyway just for practice, but we already know. This is a +5, we don't even have to do it again, and a -2 on the oxygen. And then the aluminum is monatomic ion, so it's a +3. So now we've identified all of the oxidation numbers on each atom of the whole balanced equation, all the reactants and products. Now we look for changes. And iron is going from a +2 to a 0. So I know that iron is involved in the redox because the oxidation numbers are changing from reactants to product. And so if I'm going from a +2 to a 0, I look at the number line, put 0 here, 1, 2, plus 1, plus 2, negative 1, negative 2. So here we have a number line, and I'm starting at plus 2, and I'm going to 0, so I'm going this way on the number line. And when you go that way, you're getting more negative. That means you're getting reduced. You're gaining electrons. And so gaining electrons, reduction. When you gain electrons, you're being reduced. So now we know one of the answers, that iron's being reduced. In this redox reaction. So we know we have a redox reaction, so we already have one change. So now we also know that there's going to be an oxidation, because we learned you can't have one without the other. So now we see, I'm going to erase this for a minute so I can have room for arrows. We see the aluminums, each aluminum is going from a 0 to a plus 3. So aluminum is going from a 0 to a plus 3. And so now we look at our number line again, and aluminum starting at 0 and going to a plus 3. And so as you get more positive on our number line, that means you're getting oxidized. You're losing negative charges, electrons, and you're getting more oxidized. And so this will be oxidation. Okay, the loss of electrons. So now that's the other answer. Aluminum is getting oxidized. So that's the answer to the problem. Using oxidation numbers, we've shown our work, and we've shown that the iron atoms are getting reduced from reactants to products, and the aluminum atoms are getting oxidized from reactants to products. And you can see the nitrate's not even participating. Plus 5 nitrogen, plus 5 nitrogen, negative 2 oxygen, negative 2 oxygen. So nitrate in this case is a spectator ion. Okay? So you should be able to, there's some homework problems assigned in Master in Chemistry, and this is how you do them. Okay, when they ask you what's being reduced or oxidized, you determine the oxidation number on each atom, and then you see if any are changing from reactants to products. If they are, then you know you have a redox reaction, you can answer the question. Sometimes the answer could be, oh, this isn't a redox, so nothing's being oxidized or reduced. So good luck with those homework problems, a very important concept. Okay, now we're going to go ahead and go to our activity series again. So let me turn on the projector. Erase first. So let's look at our activity series again. And this is in your book, once again. And let me get the page number, page 136. So this is page 136. And you'll be given this table on the exam to do single displacement redox reactions that we talked about previously. But you need to know how to use it. And once again, this is called an activity series. And what this means, the way they could have written these as reductions or oxidations, but they decided, okay, we're going to write this. These are half reactions we talked about, and they're all written as oxidations. Because remember, any half reaction in certain reactions can either be an oxidation or reduction. You can flip these. You can leave them as is, an oxidation, or you can flip them as a reduction. And so that's why they wrote them all as oxidations, because you can manipulate them by flipping if you need to for a redox reaction. And as you'll know, it says ease of oxidation increases. And so the higher the half reaction is up on the table, it means the more it likes to lose electrons and be oxidized. So lithium likes to be oxidized more than any other element on this table. And so you'll notice everything on this table are metals. The neutral forms are on the left, and then they show an oxidation reaction where they form a cation on the right, plus how many electrons they lose. Because remember, look at manganese. Manganese, if it's going to be an oxidation half reaction and a redox reaction, it would like to lose 2 electrons and become manganese 2+. Now there's 2 more protons and electrons in the atom, and then it will give away these 2 electrons to something that wants to be reduced. Okay? And so these are just the names of the neutral species on the left. And you'll see there's one nonmetal on this table, hydrogen gas, H2 gas. It's still the neutral form though. It's still elemental form with an oxidation number of 0. So these are all elemental forms on the left, and they're neutral, and their oxidation numbers are all 0 because they're neutral, because they're elemental form. And with this activity series, if iron gets reduced in your redox reaction using this table, it's always going to become iron 2+, because that's what's on the table here. So you'll always know what the charge is on these ions using this table if you're doing a single displacement redox reaction. Look at the charge that's going to become here. Because some of them can have more than one charge, but for these single displacements, we're using these charges. Okay? And you can always figure out the electrons, because the aluminum is going to be a 3+, it means it's going to go from neutral to 3+. It's going to give away 3 electrons. And one thing I didn't mention last time, in a redox reaction, electrons lost equal electrons gained. Okay, you can't just have electrons floating around. And so we have to balance electrons lost equal electrons gained. And then you add the half reactions, and then you won't see the electrons in the final redox reaction when you add 2 half reactions, because electrons lost equal electrons gained are just like net ionic equations. They're like a spectator, and you subtract that amount of electrons from both sides algebraically, and you don't see them in the final net redox reaction. Okay. So what I'm going to do, I'm going to give you a little bit of understanding, which I was starting last time, and then I'll do it the way the book does. And the take-home message is, we can combine any of these 2 half reactions to see if we have a redox reaction. But the only time we'll have a redox reaction is if we flip one of them to be a reduction, because we have to have an oxidation and a reduction. And for it to go and be spontaneous, we can only flip the reaction below the other one. The top reaction will be an oxidation. You leave it as is. And so let's look at zinc here. If we want to get a redox reaction with zinc, metallic zinc, and leave that as an oxidation, we can flip any half reaction on this table and make it a reduction, and it's going to go. It will be spontaneous. Because we're saying zinc likes to lose electrons more than any half reaction below it. Okay? And so zinc's saying, okay, if you want to flip your half reaction and take my electrons, I'll be happy. I'll be more stable, according to this series. So let's do it. And so we can take any of these reactions and flip them, and then balance the electrons, add them together, and get a balanced net ionic redox reaction. So let's go ahead and practice that. Let's write our zinc half reactions. Zinc solid goes to zinc 2+ plus 2 electrons. That's an oxidation, right? Losing electrons. You go from reactants to products. And let's just go, boom, we're going to react with tin. But remember, to have a reaction, we have to flip this one. And so we take tin 2+ plus 2 electrons going to tin metal solid. And now, before we can add these, we have to balance the electrons. So you'll notice the electrons are already balanced here. You're losing 2 electrons, gaining 2 electrons. So we don't have to use any multipliers in these half reactions before we add them, because electrons lost already equal electrons gained. So when we add these algebraically, we're going to subtract 2 electrons from both sides. And now you keep all the reactants on the reactant side, bring them down, all those terms, and all the product terms down to the product side to get our total redox reaction. So here we go, zinc solid, whoops, not too nice, plus tin 2 plus, aqueous, because it came from a salt. And the anion of that salt is just a spectator, so we don't even need it. And now they're going to switch places. Zinc's going to become zinc 2 plus, aqueous, and tin 2 plus is going to become metallic tin. And so you'll notice we used all the terms. The ones that didn't cancel, we put all the reactant terms of the half reactions on our net equation here on the left side, and we put all of our product terms when we added on the product side. So this is our net reaction where we've added oxidation and a reduction half reaction. And so once again, this is single displacement because this was in a salt and the zinc displaced the tin out of the salt and became the anion that would form a salt if you take the water away. And then the tin and the salt became the neutral metal. They switched places from the neutral metal to the salt. So this is single displacement redox reaction. And it's a pattern that we're learning with this activity series. And so there's the net ionic equation for this redox reaction. And if the electrons lost equal electrons gained, it's going to be balanced, 1, 1, 1, 1. But if the electrons, we're going to do another one in a minute where the electrons lost is not equal to electrons gained, and then we're going to have coefficients to balance the half reaction because we have to balance the electrons. So let's do one of those. And so let's take tin again. We'll take zinc, sorry, let's take zinc again. And it's going to be the oxidized species. And it's always zinc 2 plus. So there's the oxidation reaction for zinc from the half reactions. And now let's take chromium. And to have a reaction, once again, the bottom half reaction we have to flip to get a redox reaction. Because zinc likes to give up electrons more than this one does, so we're going to flip this and let zinc give up the electrons and let the chromium 3 plus gain it, become the chromium metal. So let's go ahead and flip that. So we have chromium 3 plus 3 electrons goes to chromium solid. Okay? So there's our half reaction flipped for chromium. And once again, we have to flip the bottom one or we won't have redox. We've got to have oxidation and reduction. So now, here we have to use a multiplier because electrons lost does not equal electrons gained. So the magic number of 2 and 3, like balanced equation, is 6. So we're going to multiply this half reaction by 3, every term in there by 3. And then we're going to multiply each term in here by 2. And then we'll get 6 electrons lost and 6 electrons gained. And that will give us empirical coefficients because we're getting what the lowest common multiple, I can't remember the term. And so now let's go ahead and do that math. We've got 3 zinc solid going to 3 zinc ions plus 6 electrons. Okay? And now we multiply each term here, that's algebra. 2 chromium 3 ions plus 6 electrons going to 2 chromium, 2 moles of chromium atoms, solid metal. And now we can add them. Because when we add them, we can subtract 6 electrons from both sides, and now the electrons lost equal the electrons gained. And so now we bring all our terms down. Like before, the order doesn't matter. We got 3 zinc solid plus 2 chromium 3 plus goes to 3 zinc 2 plus 2 chromium solid. So there's a redox reaction, and once we balance the electrons lost and gained, we have the coefficients will work out from our multiplication. There's a balanced net ionic redox reaction. Balanced net ionic redox reaction. Okay? And so that's the pattern. And that, now let's do one with zinc. So let's write our zinc again. Zinc solid going to zinc 2 plus 2 electrons. Let's see if we can react it with sodium. Let's go ahead and flip it. Sodium, because the other one has to be flipped. We're going to keep zinc as a redox reaction. Sodium plus 1 electron goes to sodium solid. So what we do, if you're given a problem like this, it wouldn't look like that. It would look like this. Zinc solid plus, let's say, sodium chloride. This is what the reaction would look like. They'll give you both reactants. And they'll say, if a redox reaction occurs, complete the reaction and balance the equation. And I don't care if you give a net ionic equation or a balanced molecular, it doesn't matter. If you can predict whether one occurs and balance it, that's fine with me, as far as we are right now. And so first of all, see what they're saying here, you know this is a salt, so really that's Na+, right? Because when it dissolves in water, the ions separate. And we've got sodium ion and chloride ion. And so you always want to see what the cation is so you can find it on the table. So uncross over subscripts and write the cation, or look here and find the cation. See here's sodium, oh, it's going to be Na+. So now, first of all, you say, do we have a reaction? So locate the two half reactions on this series. There's one of them, and there's the other. Okay? And the metal has to be the oxidized one. So this one has to stay. The one they give you as a reactant that's neutral, that has to stay. You're not allowed to flip it if there is a reaction. Okay? So now you say, we learned that the only time you get a reaction with zinc is flip one below it. But here, they're asking us, can we flip one above it and have a reaction? The answer is no. They're already, in the series, zinc likes to lose electrons more than sodium. I mean, sodium likes to lose electrons, more than zinc. So sodium's going to say, I'm not flipping for you because I like to lose electrons more than you do. And so there's no reaction. They're going to stay zinc and sodium. Okay, they're already electronically favorable not to switch or participate in redox because they're already happy. Okay, so here you write no reaction. No reaction. And sometimes I say it another way, like in lecture. See, here it's zinc solid. So I circle zinc solid. And here it's Na+ in our reactants. So what you do, another way you can look at it, you locate your reactants in the activity series. Okay, and so since Na+ the cation, I put it up here. Since zinc is solid, I go to the neutral, circle the neutral. And the cation has to be below the neutral species to have a redox with that reaction. And here the cation's above. So we're going to get no reaction. Okay, the cation has to be below. That means we flipped it. Since it's a reactant, it means we already flipped it. But the problem is we can't flip this one because the series says this one likes to lose electrons more than this one. So that's a no reaction. If the cation's above the neutral, you just put no reaction. If the cation's below the neutral, then you complete the single displacement and then balance. Okay? So let's do a few of these. Let's practice a few of these now. Okay. First one, let's take nickel, solid, react it with lead nitrate, lead 2 nitrate. Okay. And so here are the two reactants. Now the question is there a redox reaction with these species? And if there is, complete and balance. So we know this is really lead 2 plus. So this is aqueous. And we know this is lead 2 plus aqueous because the 2 right there. I'm crossing over. And so we're going to look at the table now. And so if this lead 2 plus is below the neutral nickel, they're going to switch places. If the lead's above nickel, there's no reaction. So let's look at the table. I know it's going to be hard. Here's lead. Here's our cation right here. And nickel is right here. So sure enough, the cation's below the nickel. So sure enough, we flip this and make it a reactant, so we're going to have a reaction. Or we're saying this will stay as is, and then we flip the bottom half reaction for reduction, and we get a reaction. Sure enough, that's favorable. So let's go ahead and complete it, because the cation's below the neutral. They're both reactants. So now the nickel is going to become nickel 2 plus, and see the nickel is going to, 2 plus is going to react with the nitrate. Those two ions are going to bump into each other and then make a neutral formula. So you know nickel's 2 plus because nickel 2 plus right there. And we know 2 loss, 2 gain is going to be 1, 1, 1. There's not going to be any coefficients except 1s. So these are going to come down like this. That goes into the salt. We're doing balanced molecular. And then the lead's going to come out as a neutral metal. And it should be balanced. Whoops. 2 nitrates, 2 nitrates, 1 nickel, 1 nickel, 1 lead, 1 lead. So sure enough, we did have a reaction. We completed the redox reaction, single displacement. And there it is, and balanced. 1, 1, 1, 1. Okay, let's try another one. Okay, this time we're going to take my favorite metal, gold, which I had some in today's economy, and we're going to react it with silver nitrate. So once again, if there's a reaction, we're going to complete it and balance it. If there's no reaction, write no reaction. So here the cation's silver in the reactants. So we're saying this reaction is only going to go on the series if we have gold here and if we have silver down here on the right side below it. That's what it's got to look like for this reaction to occur. If the silver is above it, then there's no reaction with this silver ion. If it's silver ions below it, then there's a reaction. Okay, so let's find out. Let's look at our series. Oh, and gold's way down here. So in other words, in this table, for gold to react, it's got to flip because it likes to keep its electrons more than any other element on this table. And so here's gold solid. Oh, and here's silver ion. And uh-oh, no reaction here, right? Because the cation is above the neutral. Or we can say gold can only be oxidized if the one below it is reduced, but there is none below it. And so we can't flip the one above it to give it Ag+. So we know that there's no reaction here. So here we don't have to make any products in balance because there's no reaction. Okay? And that's why gold is so stable, see? It doesn't like to lose electrons compared to a lot of things, so it keeps its electrons and stays real shiny. Because remember, the cations have totally different properties than the neutral metals. So that's why gold's a real shiny metal and really stable. It likes to keep its electrons. Okay, let's do another one.